Hey everyone, have you ever stopped to wonder how mathematics actually makes sense of, well, everything? It's like it has a secret language, a kind of foundational code that it uses to organize the entire universe. And today we're going to crack that code. We are diving deep into set theory, and you're about to see how these really simple ideas build the powerful logic that runs our world.
So let's just jump right in with this big question. How does it do it? How does mathematics take all the beautiful, messy chaos of reality, from galaxies all the way down to algorithms, and give it some kind of structure? Well, the answer, and this is the amazing part, starts with a concept so simple it's kind of brilliant.
All right, let's get into it. We're going to start with the most basic unit you can imagine, the very first building block in this entire language of logic, the set.
So, what in the world is a set? Well, it's exactly what it says here, just a collection of distinct elements. Seriously, think of it like a bag or a box or a folder on your computer. You can have a set of your favorite songs, a set of planets, a set of primary colors. The one key rule, every single item inside has to be unique. No repeats allowed.
Okay, so once we've got our container, our set, we'll probably want to know how many things are inside, right? That's where cardinality comes in. It's really just a fancy word for counting the number of elements in a set. So if your set of primary colors has red, yellow, and blue, its cardinality is 3. It's as simple as that. Now, it turns out that sets pretty much come in two main flavors. On the one hand, you've got your finite sets. These are collections you could, eventually finish counting, like the days of the week. But on the other hand, you've got these incredible infinite sets, which just go on forever. Imagine trying to count all the positive whole numbers. You could count for the rest of your life, and you would never, ever find the last one. Okay, this is where things start to get really interesting. You see, sets aren't just a bunch of isolated boxes. They can actually contain other sets, creating these cool layers of organization, almost like those Russian nesting dolls. So let's talk about these sets within sets. So that smaller doll on the inside, that's what we call a subset. A subset is just a set where every single one of its elements can also be found inside a bigger set. For example, the set that just has the vowels, A, E, I, O, U, is a subset of the entire alphabet. Makes sense, right? Now, there's a subtle but really important difference here. A regular old subset, as you see on the left, can be a perfect copy of the original set. But a proper subset, over on the right, is a little stricter. It has to be smaller. It can't contain everything the original set has.
And this simple idea leads to something kind of mind-blowing. Let's say you have a tiny little set with just 3 items in it. How many different subsets do you think you can make from that? The answer is 8. There's actually a formula for this, 2 to the power of n, where n is the number of items you start with. It just goes to show how quickly possibilities can explode from even the simplest beginnings.
And what do you call that big collection that holds all 8 of those possible subsets? That, my friends, is the power set. It's like the ultimate set of all sets, the meta-container that holds every single combination you can possibly make.
Okay, so we've got our sets. You can think of them as the nouns of our new language. But how do we get them to do anything? How do they interact? For that, we need verbs. And in the world of mathematics, those verbs are called functions.
Now, a function isn't just any old connection. It has to play by some very strict rules, what we're calling the 2 golden rules. Rule number 1. Every single element in your starting set, your input set, has to be used. Nobody gets left on the bench. And rule number 2, each of those inputs can only go to one unique output. It can't be indecisive and point to 2 different places at once.
Let's see if this example follows our rules. Okay, look at set A. Is every item being used? Yep, 1, 2, and 3 all have arrows coming out. So rule 1 is a check. Now, does any item have more than one arrow coming out of it? Nope. Each one just goes to one place. Rule 2, check. So this is a perfect, valid function.
So now that we know what a function is, we can actually start to classify them. And the 2 most important types you're going to run into are one-to-one and onto. They basically just describe how the connections between the sets are behaving.
So, a one-to-one function, sometimes called injective, is very, particular. Every input has its own dedicated, unique output. The big rule here, no sharing. No 2 inputs are ever allowed to point to the same output. And you can see exactly how this works here. Notice how each input from set A, 1, 2, and 3, points to its own private output in set B. And see that element D over there in set B? It's totally fine for it to be left over. That doesn't break the one-to-one rule at all. Now, an onto function, or surjective, has a totally different goal. Its main priority is to make sure the entire output set gets used. Every single element over in set B has to get hit by at least one arrow from set A. No outputs can be left feeling lonely.
And this is a perfect picture of it. Look closely at set B. Every single item, A, B, and C, has an arrow pointing to it. It doesn't even matter that B is being hit by two different inputs. As long as the entire output set is covered, it's an onto function.
You know, this leads to a really simple but super powerful shortcut. A lot of the time, we can predict what kind of function is possible just by counting. For a one-to-one function, you can have more inputs than you have outputs. And for an onto function, you need to have at least as many inputs as you have outputs, or more. It's a neat little trick.
And that brings us to the perfect match. What happens when a function is both one-to-one and onto? Well, you get a perfect pairing. Every input has its own unique partner on the other side, and nobody in the output set is left out. This very special kind of function can only happen if both sets have the exact same number of elements.
So, okay, we've talked about sets, subsets, and all these different functions. But let's take a step back. Why does any of this abstract alphabet even matter? What's the real big picture here? Well, what we've been learning is quite literally the language of logic. Set theory is the invisible bedrock for almost all of modern math. It's the hidden blueprint behind computer science, telling us how to build databases and how algorithms should think. Ultimately, it gives us a crystal clear, universal way to describe complex relationships in pretty much any field you can imagine.
And honestly, we've only just learned the alphabet today. As Dr. Gajendra Purohit, whose work inspired this whole thing, says himself, these are just the basic definitions. From these simple building blocks, a whole universe of theorems, proofs, and incredible discoveries is built.
So I'm going to leave you with this final thought. If sets are the nouns in this language of logic, and functions are the verbs that create all the action, just imagine the kinds of incredible stories that mathematics can tell about our universe.